Hi everyone, I'm Zhuoshu. Today I want to talk about kidney exchange from an application point of view, thinking about what happens when we extend kidney exchange to include compatible pairs, where in those pairs the patients can be matched with the donors directly. This is a joint work with our awesome RU students, Kelsey, William, and Sofia, and kidney transplant surgeon Jason Wellen, and professors at CSE department, CJ Hall and Sanmay. Okay, so in today's talk, I'm going to focus on two dimensions of this application. The first one is because we want to convince the compatible pairs to join the kidney exchange. As we know, those pairs can do the internal match directly. So we need to tell them how much they can do better as an incentive. To answer this first question, what we do is to first explicitly include matching quality into kidney exchange and build a simulator based on that to study the benefits under different settings and assumptions. The second thing we tackle is when compatible pairs come to the kidney exchange, because they can do the internal match immediately, they are unlikely to wait any longer. So this is a pessimistic assumption, but this is a good start point because this is close to the reality. Under this assumption, we design a hybrid static dynamic matching model to help us capture the need of immediacy. So here we use the static pool to represent the incompatible pool and the dynamic pool to capture the impatient compatible pairs. We also design an algorithm which based on online prime dual algorithm to help us solve this kind of problem for this situation. Here's some spoiler. So overall, by including compatible pairs, we can match 50% more incompatible pairs. And also, we can increase the expected graft survival of compatible pairs by 1 to 2 years. OK. Let me start by giving you some background of what happens in living donor transplantation. Every year, there are roughly more than 100,000 patients waiting for kidney transplantations. In 2014, which is the latest year we have numbers, 17,000 kidney transplant has been conducted, and 1/3 of them are from living donors. As we know, the problem of living donor transplantation is that they may not be always medical compatible. When this happens, we call this pair incompatible. One idea was proposed decades ago is to send those pairs to the kidney exchange. Kidney exchange allows patients who suffer from terminal kidney failure but has been lucky enough to find a willing but incompatible donor to swap donors. One of the most important things in kidney exchange is to have more matches. So there are a lot of great work focusing on designing better algorithms to keep improving the situation. But there has been less focus on modeling match quality. So this is what we are focusing on in our paper. When we're taking matching quality into account, it's easier for us to incorporate in the compatible pairs because we can easily trade off between different matches and also provide an incentive to the compatible pairs by telling them how much they can do better. So the first thing we want to solve is what kind of metrics we should use to measure the matching quality for the living donor transplantation. It's pretty nice people have been thinking about these issues recently. A team from JHU has proposed a numerical measure called LKDPI to measure the quality of living donor transplantation. And these measures depends on the factors, both specific to the donor size, like donor age, donor sex, SPP, and so on, and also the donor-recipient match characteristics, like LKDPI mismatches and ABO incompatibility. OK, now we have the quality measures, LKDPI. Then we want to be more explicit on how beneficial it can be, it can be to consider the match quality. The answer to this question is largely depend on the heterogeneity of match quality across pairs. At one extreme case, we can see from the left graph, we use the edges to represent the match quality in a pair, and one side is the patients and the other side is donors. So for the left graph, we can see the match quality is completely depend on the donor side. So this is a completely homogeneous case. Basically, we have no benefits from the trade. But at the other extreme, which is the right graph, we have the completely heterogeneous situation. Basically, everything is idiosyncratic, and we can have the maximal gain from trade. So what's the situation in reality? Here is how we proceed to answer these questions. Let's first not even worry about the incompatible pairs, just focus on the compatible pairs. We take the compatible pairs that were transplanted in our transplant centers over the course of a few years, and we swap among them. And we're just wondering, can we improve the match quality overall? We look at two situations. The first one is the optimal situations where any donor can match with any recipient. And the other one is the traditional 2 and 3 cycles, which are used in the kidney exchange. So one thing to note in both situations, we impose the Pareto improvement restriction. So far, so good. OK, so here's the results, which shows the distribution of LKDPI. So for the LKDPI, the lower number means better match and longer graft survival. So comparing to the original matches, which are the yellow bars, we can see the optimal match, the blue bars and the 2 and 3 cycle swaps greatly shift the distribution to the left, which is good. The other thing worth pointing out is that LKDPI is calibrated that 50 is the mean quality of the cadaveric kidney transplants. Conventional wisdom always saying that the living donor transplantation should be much better than the cadaveric transplantations. That turns out not to be true in this data set, because we can see a lot of transplantation has a LKDPI larger than 50. This means that the recipient is getting a kidney from a living donor, which is actually worse than the average cadaveric kidney. This fact is very surprising to the surgical team that we will work with, and this also shows there should be serious potential for improvement and great gain from trade. Because LKDPI is a percentage measure and it's weird to add them up as an object to optimize for us later, so we take the LKDPI index and reverse engineer to come up a fitted model of what's the expected graft survival given LKDPI. And we use this as our measure to figure out whether we can improve the situation by doing better matches. OK, now let's turn to our main questions. Think about what would happen if we incorporate compatible pairs in kidney exchange with incompatible pairs. There are two things we can think about. One is how many more incompatible pairs we can match with, which is the traditional question in kidney exchange. And the other one is how much better the compatible pairs can do. We measure it by how many years increase of expected graft survival. In order to answer that two questions, we need some ways to generate counterfactuals. So the first thing we did is to develop a simulator to generate those patient-donor pairs. And this simulator has two characteristics. One is whether a pair is compatible or not. This depends on the standard Sanmay simulators. And the other one is the characteristic for calculating LKDPI, which is generated based on the estimated joint distribution based on data set from our transplant center. Now we need to simulate the match process. As we say, the compatible pairs are unwilling to wait any longer, even in order to find a better matches. So in order to study the minimal departure from the current practice, we introduce a hybrid matching models where the incompatible pool wait for a match to be run out of the pool, and the compatible pairs are impatient and match greedily. Let me show a talk example of what would happen. So we have a bunch of incompatible pairs, and we use those dots to represent the patient-donor pairs. And so the edges between them are the sum of potential, sum of qualities of potential transplantations. So at every point in time, a compatible pair is joined in the market. Say at time t is equal to 1, I get a pair that arrives with the internal match with quality 5, and also a cross pool transplantation with a quality sum of quality 10. So now the algorithm decides not to do the cross pair, just do the internal patch. So this compatible pair leave the market. I come to the step 2. Now I didn't get any across pool transplantation, so we do the internal match. We come to the step 3. Now we have a similar situation across pool with a quality 10 and the internal match. Now the algorithm decided we do the across pool match, so we can see the incompatible pair also leave the markers. And I come to the next step, same situation here. Let's say we are reaching the end of periodical time, and here we just run a match on the remaining pairs. So we can see this to leave the market. Okay, so now is the time to think about what kind of algorithm to use in this kind of matching. Instead of using the traditional gradient batching mechanisms, we consider relaxed IP formulation because this can help us to estimate the value of a incompatible pair, and also when we should match the incompatible pair with the incompatible pairs. Here I will use a simple 2-cycle matching case as an illustration. We define this Wi as the match quality of a pair, and x and I is the match variables. So I will get n and I shortly. So basically, T is we define the T as the online agents, those compatible pairs. Basically, this constraint is saying that each online agent either match with itself to the internal match or match with the standby incompatible pairs. And we then use the I to represent the incompatible pairs. So this constraint is saying that each standby agents match exactly with one other agent. And we use this N to represent all the agents, basically the incompatible and the compatible agents. So here we go back towards SI. SI means the match variable for any pair. So it is either match with an incompatible pair or do an internal match. Okay, so this is the overall formulation for the 2-cycle matchings. And we just know that it's very easily to extend with k cycles and even chain. The due of this linear program can be written as following. So the alpha t is the dual variable corresponding to the compatible pairs, and beta I is corresponding to the incompatible pairs. So those dual variables can be interpreted as the value if we leave those pairs alone. So we can also think about the shadow price in the normal online prime dual algorithm. So we call this dual variable as shadow survival. So given the optimal beta I, we now can have the online assignment rule. So basically, we have our algorithm called online dual assignment using shadow survival estimation, which is all dice. In practice, we don't know the optimal beta I. We need something to estimate them. We do that by using machine learning algorithm, where we first creating training data set by our simulator, where those true beta I is generated by solving the Oracle version of relaxed integer program problem. And then once we have those training data set, we just train the machine learning model on 2 sets of features. One is the demographic information of the incompatible pair, and the other one is the initial graph state of the incompatible pool. And we can see from this figure, this algorithm is doing pretty good job on predicting true beta I. Okay, so let's finally go back to our main question and see the final results. We want to see whether we can increase the number of matched incompatible pairs and whether we can improve the situation of the compatible pairs. Here's our main result. We first set the baseline as the compatible pairs doing the internal match, and the incompatible pairs run the kidney exchange along, doing the 2 and 3 cycles kidney exchange. So we can see the baseline match like 50% of incompatible pairs. And our ODS algorithm is matching 70% incompatible pairs. So we can also look at the Oracle algorithm, which is the best one could possibly do with the future knowledge, which is matched like 76%. And we can also be close by using an algorithm similar to ODS we call NetOS, which is a method that explicitly solves the integer program for every arriving compatible pairs. So this is kind of computationally expensive, but this makes us close to the Oracle solution. Okay, let's see the performance of compiler pairs. The baseline has a 9.6 years graph survival, and we can see the ODAS algorithm increase that by 1.5 years. For the performance in compiler pairs, there is a small decline for the expected graph survival, but this is conditional on the matched population. So basically, we are matching many more. We can also ask the equity or justice question. So one community we usually worry about is the O-type recipients. That is harder to match than other blood types. And we can see we almost double the match population of the incomplete pairs with blood type O recipient. And this is actually more than the relative gain for the general population, which is shown in the left. Another thing we can look at is the performance from an algorithm perspective. So the objective here is the total expected graph survival. We can see that ODAS algorithm, and in fact, all the online algorithms are very close to the Oracle, which has the full future knowledge. Okay, so in conclusion, our main contributions have several faults. First, we present a framework for studying key exchange in weighted or cardinal utility setting. And then we use this framework to estimate the benefits of incorporating compatible pairs to the key exchange. And to consider the practical implementation, we design a hybrid static dynamic matching model, and we also design a corresponding algorithm to solving the problem in this situation. So basically, we see there are a lot of gain by incorporating compatible pairs, and we should do that. So we leave some future directions we want to proceed. So this is overall I have. Thank you so much.